Good day, everyone. This is the presentation of Classwork 1 of the students of RTU BSECE CEIT 29601P. So the Classwork 1 contains the following topic. First is the information or channel capacity. Second is the Shannon limit. And third is some sample problems. So the team is the following reporters. I am Kyla Espina and my partner will be Michelangelo Sabularse. So the first topic is the information or channel capacity. So let us first define channel capacity. Channel capacity or C is defined to be the maximum rate at which information can be transmitted through a channel. The fundamental theorem of information theory says that any rate below channel capacity, an error control code can be designed whose probability of error is arbitrarily small. To define more and to know more about this, in electronic communication channels, the information capacity is the maximum amount of information that can pass through a channel without error. It is a measure of channel goodness, and Shannon information or C has been long used as a measure of the goodness of electronic communication channels. So this was first introduced by Claude Edward Shannon, and he was an American mathematician, electrical engineer, and a cryptographer known as father of information theory. So to understand more deeper, let's discuss the Shannon limit. Shannon limit for information capacity. Here we can see a figure which has a line graph of Shannon capacity. And in the x-axis is the bandwidth in hertz, and in the y-axis is capacity C bits per second. And it says here that the higher the noise to ratio, the higher the signal to noise ratio here, and the more bandwidth, channel bandwidth, the higher the possibility data rate. And this is confusing at first, and to make everything clear, we can see it using the formula. So this is the formula, and C stands for the channel capacity in bits per second. B is the bandwidth of channel in hertz, and Sn is the signal to ratio or the carrier, which is in watts. So if you were given an S over N in decibels, you have to convert it into watts. Here, one can receive a signal with noise in every session because of noise is there and the channel will receive signal and noise both together. So for my part, or the first half of the discussion, that would be all. And the third part would be explained by Mr. Sabulars.
Michelangelo Sabularsi. I'm here to discuss some sample problems in channel capacity. We have four problems here for our classwork number one. So problem number one. For a typical telephone line with a signal to noise ratio of 30 decibels or 30 dB and audio bandwidth of 3 kHz, maximum data rate is how much? So first, we need to identify in the problem what was the given or our given. For our SNR or signal to noise ratio, we have 30 decibels. For our B or bandwidth, we have 3 kHz, and C is the unknown value. So we can use the formula of channel capacity is equals to B log 2 1 plus SNR or S over R. First, in SNR, we cannot use in terms of dB. So we need to translate or convert it in terms of data or value. So this right side of the presentation, the conversion of dB. If you have 10 dB is equals to 10. If you have 20 dB equals to 10 to the power of 2, 30 dB 10 to the power of 3, 40 dB or 10 to the power of 4. So in our problem number one, we have 30 dB. So we use the 10 to the power of 3. You can direct substitute into our formula, which is 3 times 10 to the 3 because it's kilohertz log base 2, 1 plus 10 to the 3. And if we calculate 1 plus 10 to the 3, it will give us 1001. So the next formula is 3 times 10 to the power of 3 log 1001 over log of 2. Base 2 means we need to divide it by log 2. So if you calculate this formula, the third part, you can sum up that our capacity is 3 times 10 to the 6 bits per seconds or 3 Mbps. Our problem number 2. For a Gaussian channel has a 1 megahertz bandwidth, calculate the channel capacity, the signal power to noise spectral density is 10 to the power of 5 per kilohertz. Also, find the maximum rate. So we need to find again the given, which is our beta, or I mean bandwidth is 1 megahertz or 10 to the power of 6 in terms of hertz. Our SNR value is 10 to the power of 5 as a given in the problem. Then our channel capacity is unknown value. So if we substitute into our formula, which is C equals to B log the power base 2, 1 times 1 plus SNR, which is 10 to the power of 6 log base 2, 1 plus 10 to the power of 5. 10 to the power of 5 is equals to 1 plus 10 to the power of 5 and is equals to 10001 is equals to 10 to the power of 6 log 10001 over log 2. So if you calculate this 10 to the power of 6 log 10001, you can sum up with a 16.6 times 10 to the power of 6 meters per second. The question from problem number 2, find also the maximum rate. And so if we have find the maximum rate, we need to sum up the formula, which is 16.6 Mbps in bits per second. Our problem number 3. For a satellite TV channel with a signal to noise ratio of 20 decibel and a video bandwidth of megahertz, find the maximum rate. I think it's 10 megahertz for our bandwidth. Again, for like problem 1 and 2, we need to identify what's the given. For our SNR, we have 20 dB or 10 to the power of 2. For our bandwidth, we have 10 megahertz, which is equal to 10 times 10 to the power of 6 in terms of hertz. And our capacity is unknown. Again, like problem 1 and 2, we need to direct substitute it to our formula, which is C is equal to B log base 2, 1 plus SNR is equals to 10 to the times 10 to the power of 6 log 2 base 1 plus 10 to the power of 2. If you calculate this into our calculator, you have a sum of 6.6 times 10 power of 7 bits per seconds or 66 Mbps. For our last problem, problem number 4, calculate the channel capacity with the bandwidth is equal to infinity. So here, our bandwidth is infinity. As a channel capacity formula, C is equals to B log to the base 2 times 1 plus SNR, S over N, or signal to noise ratio. So, if you have 2 noise power of N is equals to theta B, where N over 2 is power of density. So, if we place the N is equals to theta B, our channel capacity formula, we can sum up with C is equals to B log base 2, 1 plus S over N or theta. Our B is our bandwidth. So, we need to do the power S over N over B. This portion is to transfer it to a coefficient. So we can sum up with N B over S times S over n log base 2 1 plus S over n to the b, or data bandwidth. And then we can, if we try to calculate it, we need to place the S over n to the outside, which is S over n, or data n bandwidth, equals to times n over S log base to the base 2 times 1 plus S over n. Again, to continue, we need to find the limit of our bandwidth and data bandwidth. So C is equals to S over n limit if bandwidth is equals to infinity, log 2 1 plus S over nb over S over nb. We all know that S over 1 plus S over nb is a logarithmic t with the base of 2, because it says here log 2. So you can come up with a formula of S over n log of e to the base 2. And if you calculate the log of e to the base 2 is equals to 1.44. So our channel capacity is 1.44 times S over n with a bandwidth of infinity. So that's all for our presentation. Thank you again for your listening. Again, my name is Michael Sagolarse, and my partner is Spina Kyla from CIT 29601. Again, thank you.